My title is there. The picture is hell freezing over, and some of you in the crowd know why. I'm going to talk about rain on snow and some simulations I've been doing for a long, long time. To go into it, what is it? I mean, most of you are from the Northwest, or at least Westerners. You know what rain on snow is. It's the thing that ruins a perfectly good day of skiing. Or fishing, or maybe just trying to drive over the pass, for that matter. There's a really big, important ones with big storms, generally when the seasonal temperature is a little warmer than normal and you get the snow melt. They can be major water inputs in the Northwest and in Western North America. In most cases, they can exceed either rain alone or snow melt alone. Despite the name, the rain usually doesn't cause most of the melting. The energy physics are that sensible and latent heat are usually a little more important, and that's probably the last I'm going to talk about physics. Where does it mostly occur? Worldwide, it tends to be in the maritime temperate climates, but it occurs practically everywhere except in the tropics. Western North America is a really prime area for this because we've got this big, huge target here in the path of these atmospheric rivers or Pineapple Express or whatever you want to call them. They can miss Norway or New Zealand. They can hardly ever miss the United States. So winter storms from the Pacific. We have mountain ranges where there's usually snow at least somewhere. And so around here, they tend to be most common, rain on snow events tend to be most common in the middle elevations where there's snow. This is a reference you might want to look up on some data from the Western United States from a few years ago. Okay, when? Again, people have been bringing these up all afternoon, so I don't have to say much about it. We have frontal cyclonic storms coming in off the Pacific on the jet stream or on an atmospheric river. Especially when they're warm from the southwest, warm air holds more water, so you can deliver more water more efficiently. Around here in the northwest I'm talking about, most of them occur in the fall and winter, in which case the rain is usually the larger component of the water input. The snow melt is secondary. Some of them occur in the spring, so you might also already have the spring snow melt going on, and then you hit it with a little extra rain on top, and that can combine into a major event. I'll mention one in a second. And again, Madden-Julian oscillation, ENSO, PDO, all of these things affect when storms occur and when multiple storms, rain on snow events occur in one winter. I want to specify there's no specifically rain on snow storm. I mean, there's big rainstorms that might or might not fall on snowpacks, and so we need a combination of those things in order to get rain on snow. Just quickly through a bunch of the major events. If you've been here very long, you've probably experienced some of them. The Vanport flood, and those of you who aren't Portlanders, this was actually an upper Columbia Basin springtime rain on snow that caused its greatest damage right down here along the Columbia Basin in a little town between Portland and Vancouver called Vanport, oddly enough. The Christmas flood of 1964, this is a picture of the steel bridge that the MAX trains go over. Excuse the photographer, he was only 11 and it was a new camera. Several of these, I won't go into all of them, had some fatalities involved. Our latest big one, February of 1996, from my angle that picture's kind of washed out, but that's Willamette Falls upstream at Oregon City as the flood was ending. The falls were practically eliminated. Some things, November 2006 wasn't really much of a rain on snow because it came early enough that there was hardly any snow except in the Mount Rainier, the higher elevations of Mount Hood and things like that. Want to emphasize they aren't all catastrophic events. We sort of remember these, but rain on snow somewhere in the larger Pacific Northwest region is happening somewhere to some extent almost every winter. And so it's a larger sample of events that I'm a little bit more interested in. So, and then why does it matter? Well, as was mentioned just before, or in a couple of the talks, when you rake off a bunch of the snowpack, the nascent snowpack, in November and December, it's not there to be running off and helping you do things in June and July and August. So we're redistributing the seasonal water input, precipitation, maybe in ways that we don't particularly like. Sort of in an event time frame, rain on snow affects people and our stuff, things we care about, causing high runoff, big and small floods, channel erosion, fish habitat problems in some cases. The big ones also tend to be our largest episodes of landsliding and to some extent snow avalanching. And then engineering problems, excessive roof loads, collapsing buildings when you get wet, sloppy snow and the water isn't draining through the way it's supposed to, clogging I-90 over Snoqualmie Pass. And to some extent, people affect the process. I originally got into this through forest management when I worked for Washington Department of Natural Resources, but here we're talking about climate change. And every now and then, it inspires lurid headlines in the tabloid press. Here's the innocent victims, musk oxen in the Arctic tundra. So, even the American Geophysical Union is taking notice. So when we talk about rain on snow, we got to talk about a couple of things having to do with hydrologic significance. And one of them is the distinction between rain on snow and precipitation, especially, the kind of precipitation that might be registered in a rain gauge or not. If your gauge is not heated, the snow is just piling up and you don't know what's coming out of the sky. If your gauge is heated, it's going through, but on the other hand, then you don't know whether it's rain or snow necessarily. On the other hand, what I'm mostly interested is the water that's going into the ground. And sometimes that can be measured in something like a snow lysimeter here, where it's integrating not only the water that's coming through the snowpack, if any, but even the water that's coming through the canopy in this case. With hydrologic significance, we can, sort of at the trivial end of the scale, it's just a little rainwater onto the snowpack. It starts snow metamorphism and things like that, but it's really not terribly important. Some water starts leaving the snowpack, and this rather infelicitous acronym here, WAR, is for water available for runoff. So that's actually the water that's coming out of the snowpack that's going into the ground. It's not a happy acronym, but we're kind of stuck with it. And then at the larger end of the scale is an event in which the amount of water going into the ground is actually greater than the amount of water that fell out of the sky over, say, a couple of days. So in that case, I call this percent rain on snow events. Those are the ones where WAR is greater than the actual precipitation. Eventually, over the long term, the things I've been studying is to try and figure out how to get long-term frequency analyses out of these things. So I'm interested not just in how much water, little, a lot, going into the ground, the frequency, how often, and the geography of where, and the main thing I've concentrated on is the variations in elevation in a small patch of the Washington Cascades. So the problem is that rain on snow events vary due to a large number of environmental variables, climate, weather, terrain, vegetation, whether you're farther north, farther south. In essentially all cases, our observational record is too short and too scattered to be too much help in analyzing something that's this variable. And so my project has been to use probabilistic models to quantify aspects of rain on snow. I've been using Monte Carlo methods. Monte Carlo, I think most of you probably know, is use of random sampling techniques, usually in a computer model now, to obtain approximate solutions. The name was actually invented during the Manhattan Project, I found out not that long ago, and they were probably actually using roulette wheels or something. But mostly we use computers. So basically I'm running some virtual experiments to make up for the lack of stations and the shortness of the record. The computer model I created, I won't talk very much about this, but it's based entirely on Excel workbooks and Visual Basic or VBA coding. So it's off-the-shelf sort of stuff, which is about all I'm capable of handling. So in the Monte Carlo simulation, I used that for the probabilistic factors like number of storms, when the storm starts, how much precipitation, how long it lasts. And then a deterministic or physically based component to say, okay, given these conditions, temperature, precipitation, is snow accumulating, is snow melting? If there is snow and there's meltwater, tracking the percolation through the snowpack and into the ground. Since I can't make everything up, I had to actually find some data to use somewhere. The area I've been working in is kind of between Mount Rainier and I-90. Seattle's there, a little bit more of a close-up. This particular patch of western Washington was a great place to do this because it's a data-rich environment between the Seattle's watershed in the Cedar River and Tacoma's watershed right next door in the Green River. There's an exceptionally large number of weather stations, rain gauges, snow-tell sites, and things like that. So I used about 8 weather stations, including and especially Stampede Pass, this little thing up here on the Cascade Crest. It's a first-order site just south of I-90 in Snoqualmie. The sort of red diamonds are the other weather stations. And then something like, a couple of dozen snow courses and snow tells, and in some both in the same place. And those are kind of these yellow crosses and diamonds and everything else. Records I used range from 1940 to about 2005. So again, the full Monty of the Monte Carlo model. Generally, I would love to just tell you everything about it, but I've learned not to. But generally, I run it for 1,000 years, about 4,000 storms in 1,000 years. It takes about an hour or two to do a run. The assumption is for 1,000 years in this model that the climate is constant, which we're pretty sure it's not, but it helps run the system. Very simple code, and the model is based on events. It's not continuous through the year or 1,000 years, and it's based on sites, so it's not distributed across the landscape. The results of the first phase that I had done previously, and I'm going to sort of just show you a couple of different kinds of data. So in this case, elevations on the x-axis, so each one of these sets of 4 points here is the result of one elevation-based experiment. So these are the different kinds of events that can happen, starting with sort of let's start with the green line here. War equals the precipitation. These are generally most common at the low elevations because most of the time there's no snow on the ground. So it's just the rain that's contributing. Conversely, the ones where water available for runoff is 0, those are the places where either the temperature was too cold, so it was snowing, or water didn't get through the snowpack. So those are most common in the higher elevations. All of these, each 4 points has to add up to 100, so they're co-varying. The ones that are really interested is this little humpback thing here, where the significant events where water available for runoff is greater than the storm precipitation. And you can see that one is sort of climbing to a peak at around 700, 800, 900 meters of elevation and then falling back off. So this is an indication of where the prime rain-on-snow zone is based on the model, based on the data from the central western Cascades. This is another way to look at that. It's sort of a frequency diagram. So on this x-axis, we're looking at sort of recurrence interval, 10 years, 100 years. My model goes for 1,000 years, so I can speculate about the 10,000-year event. I'm not going to believe it terribly much. But the point of this graph is for the blue stuff, the 500-meter, the dashed lines represent the data for the water available for runoff. The solid lines are precipitation. At low elevations, there's about the same. It's kind of what you'd think. There isn't much snow most of the time during these events at low elevations. At high elevations, at about 1250, the water available for runoff is less than the precipitation most of the time because there's snow on the ground, it's cold, it's snowing instead of raining, the water doesn't get through. At about 800 meters, this sort of reddish line, we've actually got higher than the precipitation line. So that's the area where over a long time period, it seems, this rain-on-snow process is most significant. The previous results, before about a year ago, were that statistically, indeed, the amount of water coming out of hitting the ground is not the same most of the time as the precipitation that might be measured in a rain gauge for an event. At most elevations that I looked at, from about 200 to 1,500 meters. Didn't go lower, didn't go higher. Rain-on-snow does seem to be most important in these middle elevations, and the preferred rain-on-snow zone in the area I was looking at, grossly, it's about 500 to 1,100 meters. Bringing it finer down, it's more 700, 800, 900 meters. Okay, so that was the pre-climate change version. So now, since then, I've sort of looked at it and played around with some climate change scenarios. Generally, around here, I read people who think, temperatures are rising. We don't know what precipitation is doing so much. And snow volumes are declining already and projected into the future. So the model can be used to sort of look at these different kinds of scenarios. Again, so I just looked at changing temperatures and snow volumes. And the numbers I got were from Moat, Hamlet, and Salathe, a sort of reputable bunch of researchers, and for April 1st snow water equivalent. So the scenarios, and you'll see this CC125, basically one all the storm temperatures are increased by 1 degree Celsius, and I took the snowpacks as 90% of what the standard runs were. So you take the late 20th century data and take 90% of that. For CC2, it's 2 degrees, and snowpack as a function of elevation, kind of based on Moat et al.'s numbers from lately. And so CC5 is another 5 degree increase, and taking that snowpack and semi-randomly dividing it again by half. You can almost think that CC1 is kind of where we are now. It's not very much into the future. Okay, so I showed you this before. This was the non-climate change version. And I'm going to skip that one because this one is more interesting. So all of these lines, or each set of these points, are going to change with these various climate change scenarios that I've run with the model. So I'm just going to, I could sort of graph all of those and it looks terribly confusing, but I'm just going to concentrate on this war greater than P set of data here. As we go to climate change scenarios 1, 2, and 5, the number of the proportion of significant rain on snow events increases over a fairly broad elevation range, and it seems to go uphill a little bit. So this is, you know, what you'd expect. It's getting warmer, there's less snow, the effect is going to seem to be rising uphill, or the stations are acting lower, is another way to put it. Again, with the frequency diagram, let's get away from the 1,000-year events and just sort of concentrate on real life sort of events, 50, 100, 10 years here. This is for 800 meters. Again, the old lines for precipitation were blue, and the old war line is the dark red. As we go through these climate change scenarios, we're going up, you know, a few centimeters out of, you know, if you even look at well, let's look at the 100-year event from what we've got now to the climate change scenario, 3 centimeters on top of a 40-centimeter event or something like that. Not huge, but, you know, the critical level for a cow in a floodplain is between here and here. So the bottom line, it will be still important in the middle elevations, assuming all the model is worth a damn. For increasing temperatures, declining snowpack, it seems like we're going to get a larger proportion of rain on snow events across a broader range of middle elevations. That's what that arrow is supposed to show. And the preferred rain on snow zone seems like it's going to be moving up, and we can infer that the effects of rain on snow, whatever they might be, are liable to be moving up as well. We're never going to get to the point where we can say there's never going to be a 1996 rain on snow again because there won't be any snow at lower elevations, but possible.